5. In this case, we have 6 word symbols 1, 2, 1, 3, 3, 4. Then if we take an element Z0 to Z5 that is in C6 minus 0, I mean non-zero element in C6, there we can see that Z will be in PL24 if and only we satisfy this Fluker coordinate, this Z0 Z5 minus Z1 Z4 plus Z2 Z3 equals to 0. And then a weight vector is called Fluker vector if and only if this satisfies B0 plus B5 equals to B1 plus B4 equals to B2 plus B3. Okay, so for this Fluker vector, we can define, then this, since this PLKN is stable under with respect to this action, we can define the weighted Grassmannian, like we can define a space weighted GRBKN that is just PLKN quotient by this weighted V action. Okay. So now the interesting thing is, this space what I have defined, is it similar to the spaces weighted GRDN defined earlier? You know, we can, okay, so we can take a weight vector W equals to W1 to Wn in Z greater than equals to 0 to the power n and a positive integers a. Then if we define Bi by this way, like some a plus summation W lambda ij, where lambda is this word symbol, then B will give a Fluker vector. And this way, you can see that the weighted Grassmannians, those are defined earlier like by Abe and Matsumura and our earlier paper also. That those are already, those we can write by something like GRBKN. But is the converse also true? Like for any GRBKN, does there always exist some W and A such that W and A such that this Bi equals to Bi can be expressed by equation 6? The answer is yes, we can find some W and A, but the thing is, this W is in Z to the power n. That may not be positive, may not be non-negative integers, and A also may not be positive integers. We can see for this there are so many. I mean there are some extra Fluker vector that cannot be derived from W and A. For example, we can see these examples, like here the second component is 1. If we try to find some W and A, here W, if we fix A is positive integers, then W will be like may come the negative integers. So here these two conditions cannot be satisfied together. Like this is basically a huge a bigger class that contains the weighted GRDN that defined earlier. Okay, then now the question is how to weighted, I mean, can we permute the weight vectors such that they after permutations two weighted Grassmannians are related? Further, we introduce the Fluker permutation. If sigma be, let sigma be permutation on the set 0, 1 to m, sigma is said to be Fluker permutation if sigma b is a Fluker vector for every Fluker vector b. Like, and we can see that every permutation on Sn that induce a Fluker permutation on this set 0, 1 to m. Like this Fluker permutation set is not is a quite bigger class that contains the set of all permutations of Sn, and we can see this is a subgroup that is sitting inside Sn and Sm plus 1, that is the permutations of 0, 1 to m. Then the theorem is like, if we have a Fluker permutation sigma, then the weighted Grassmannian GRBKN that is weakly equivalently homomorphic to GR sigma b. I mean, after doing the Fluker permutations, those two weighted Grassmannians are weakly equivalent. I mean, actually, this theorem has a huge applications to compute the torsions, like to reduce the torsions from the equivariant from the integral cohomology ring, because this homomorphism will induce so many different cells, Q cell structures on this weighted Grassmannian, but I will not. And also we can get like we can have some assumptions such that we can say that this weighted Grassmannian has no torsion for a for a prime P, it has no P torsions, but I will not go in the general statement. I will consider a subclass of this weighted Grassmannian, where I will surely can say that it has no P torsions. For any P, it has no torsions. I will that the subclass is like DVC weighted Grassmannian fold. This idea was defined in this paper, our earlier paper. A weighted Grassmannian fold is called divisive. Just you add a weighted Plucker permutations on this thing. So weighted, if there exists a weighted Plucker permutation sigma on the set 0, 1, 2 m such that B sigma I divides B sigma I minus 1 for every I equals to 1, 2 dot m. Now the interesting thing is, if we have assumed a weighted Grassmann or divisive weighted Grassmann fold, then it has a sister and invariant CW complex structure with cells C to the power d lambda. Here d lambda is the length of the Schwarz symbol lambda I. Then we can say that the integral cohomology of the divisive weighted Grassmann manifold has no torsions and concentrated in even degree. So is it okay? Okay, then now since we have assumed Bi divides Bi minus 1, so we in our earlier paper also we computed the integral cohomology ring of the divisive weighted Grassmann manifold, that is defined by HTN star GRB can, integral cohomology Z is those alpha is in direction J equals to this is by the GChem computation, that J equals to 0 to M Z y1 y2 im such that y lambda I minus dij y lambda j divides alpha j minus alpha I. And also in our earlier paper we have found a basis B still lambda I of this equivalent cohomology ring as a zy1 y2 in module, and that is uniquely determined by these three conditions. First condition is like, if it has its lambda j coefficient is non-zero, then lambda j must be greater or equals to lambda I. And B is still at lambda I coefficient and lambda I component, it should be in lambda is in R lambda I, y lambda L minus BL by BI and y lambda I. And for the other component, the lambda jth component, this is the homogeneous polynomial of y1 y2 yn of degree d lambda I. Okay, now so for this basis, our target is how to compute the structure constant in the for the cohomology, for the equivalent cohomology ring, this equivalent cohomology ring. So first the idea is like, we consider B to be exactly equals to 1 every Bi is 1. Then that for that the weighted Grassmannian is nothing but the Grassmann manifold. So first we consider how this basis becomes if we consider the Grassmann manifold, and what is the relation between this basis and the basis constructed by Knudsen and Tau. There is a paper by Knudsen and Tau that they computed the equivalent cohomology ring of Grassmannian, and in the structure constant they also computed. So what is the relation between this basis and the basis computed constructed by Knudsen and Tau? And then I compute the structure constant for this Grassmann manifold, and then by some isomorphisms I have computed the structure constant for the weighted Grassmann manifold. Okay, so further first we need these permutations in Sn. This is 1 2 dot n, 1 goes to n, 2 goes to n minus 1, 3 goes to n minus 2 dot n goes to 1. Okay, I should write this C tilde Lij I should write. This is for the Grassmannian case. When b equals to if every b equals to 1, like for the Grassmannian, the structure constant is the we can I constructed the structure constant for this Grassmannian with respect to this basis. With respect to this basis, is nothing but some sigma weight p, where p is a puzzle whose with boundary this sigma r lambda is sigma r lambda j sigma r lambda l. See, the sigma r will induce, will induce a Plucker permutations. Then we can define this. Okay, first thing is here, what is this puzzle? We no need to confuse about the puzzle p. We can think here that for the puzzle p, the sigma weight p is something like product of the 1 degree polynomial, that product of some y lambda I minus y lambda f, where lambda is less than lambda f, because this puzzle is something like, I should say one thing, a triangle. If I consider a puzzle like with boundary delta lambda I, lambda j and lambda k. So for this lambda I, we have defined. For this lambda I, we can consider a sequence of 1 and 0, like k many ones and n minus k many 0, 1 in the lambda ith position, like for k equals to 2, n equals to 4. If we consider a lambda equals to like 1 4 or 1 3, then the sequence will be like at first component this is 1, second component is 0, third component is 1, fourth component is 0. If I consider lambda equals to like 1 4, then it will be look like 1 0 0 and 1. So when we want to construct a puzzle whose boundary is lambda I, lambda j, lambda k, we have to, for each boundary we have to break it by n many steps, and for each steps we have to, like, we want to put this 1 3 in the base, we want to put like 1, okay, I should put 4 steps here, 1 0 1 0, like this. And then for lambda j, I should put like 1, I also put divide its first 4 steps, then and similarly, like, and then I need to fill this puzzle by triangles and rhombuses. Those are called puzzle pieces. Then in the paper, that this is explained in the paper by Knudsen and Tau, the puzzles and equivalent cohomology of Grassmannians. So, and they have computed the structure constant for the equivalent cohomology ring of ordinary Grassmannians. So from there, I have computed this. This is the structure constant for the equivalent cohomology of ordinary Grassmannians with respect to this basis. With respect to this basis. Okay, and then by some computation, like then by using some isomorphisms, I should directly go to the structure constant here, like for structure constant for the equivalent cohomology of weighted Grassmannian is computed by this b c tilde ij is okay, so I should explain how to compute. Okay, so to compute b c tilde ij k, that means lambda I, lambda j, lambda k, what we need to do, we need to consider those Schubert symbols. Is there any question? Those are between, those are less than lambda k, those are yeah, like ijl, so I should consider those Schubert symbols. Those are less than lambda l and bigger than is lambda I and lambda j, and then we will consider those puzzles whose boundary is given by sigma r lambda I, sigma r lambda j, and then sigma r lambda q. I mean, like we fix a lambda q in between this, and then we consider the puzzles, and then for the puzzles, the mod p is the like length of the puzzle. I mean, that is defined by d lambda I plus d lambda j minus, yeah, it should be d lambda q. I mean, yeah, it should be sigma or something. Yeah, I think it will be, or is it some kind of relatable? Okay, then I have proved that this B C tilde IJL, what we have computed earlier, those are all belongs to Z Y1, Y2, Yn, because in this proof I have used some isomorphisms, those coming from the structure constant of Grassmannian. I mean, I used the structure constant of Grassmannian, then using some isomorphisms, I compute the structure constant for these weighted Grassmannians. Then I proved that these are, when it is a divisive weighted Grassmannians, this all structure constant belongs to Z Y1, Y2, Yn. Now I want to go through the what is the then like ordinary cohomology of this divisive weighted Grassmann manifold. Like since it is we have assumed the divisive weighted Grassmann manifold, it has a cell structure with even dimensional cells. So by that we can compute the first we compute the cohomology group, that is at jth component Hj is that we will take the direct sum over all I such that 2 times d lambda I is equals to j. I mean those many copies of z, and otherwise it is 0. Then we will take a basis for this equivalent for this ordinary cohomology group. We will take the basis bs lambda I, that is just the basis. I mean bs lambda I such that 2 times d lambda is j, that is a basis for the cohomology group Hj grb kn comma z. Like then first we compute what will be the case when I equals to 1, like any of them is 1, what will be the case? For I equals to 1, like b, that is all weighted pair rule. Pair rule is known for Grassmann also. This is if I equals to 1, like bs lambda 1 times bs lambda I is exactly equals to those lambda j, such that lambda j covers lambda. Here covers means like d lambda j equals to b lambda I plus 1. Yeah, this is the only, I mean that means d lambda j is greater than lambda I in this relation. And then we have computed the actual weighted structure constant for the integral cohomology ring of the divisive weighted Grassmann manifold. That is, first we consider the structure constant for the ordinary cohomology ring, that isCijl, and then I have to add some extra number, that is for each q, such that those are between lambda L and lambda I lambda j. For each q we have to consider this dqij. This dqij is also computed from the structure constant for the ordinary Grassmannian, like by this lemma. I mean, like here we can compute by C tilde Lij for all ij and L. So that using that I will compute here C tilde ij q b, and b is, here I have defined sigma or bps, that is like if sigma or p is like this y lambda I minus y lambda f, for that we just put b instead of this y. Okay, so then we can compute this dqij, and then the weighted structure constant is given by Cijl plus the summation or summation over all q, those are between lambda L and lambda ij. Some we will take sum over this dqij. Okay, maybe this is little confusing, so I will give some example here. Consider Pluckout vector, that is alpha beta, and first 3 component is like alpha beta, and last 3 components is like alpha. This is alpha and beta are any two positive integers. This is a Pluckout vector, because we can check like first component, the summation of the first component and last component. This satisfies this assumption. Yeah, this I mean I said for GR24 the weight vector is called Fluker vector. B0 plus B5 equals to B1 plus B4 equals to B2 plus B3. Okay, so then this we can see that this satisfies those condition, this vector. Then we have first we will this weight by this weighted pair rule. What will be the structure constant like Bi1 I plus 1? That is here is that is B first one is B0 plus B0 by Bi. And for the remaining structure constant, we need the help of this paper Knudsen and Tau. They have computed this structure constant for ordinary Grassmannian that like S tilde lambda 3, that is the basis as in considered by that paper. At S tilde lambda 3 times S tilde lambda 3, this can be written like this by their paper. Then we will apply, what will we do? We will apply a sigma on that formula, and then what will we get? The structure constant with respect to our basis. Then we can compute this B C, I mean like this lambda 3 and lambda 5, this structure constant, that is just structure constant for the Grassmannian of lambda 335, and then we will compute here the 433 and the again 33. I mean like because there are only two Schubert symbols, those are between lambda 3 and lambda 5, those are. So how do we get at last? This is 1 plus beta into beta minus 1. And similarly we can compute this BC225, that is exactly same, 1 plus beta into beta minus 1. And for the remaining like BC235, that will be also beta minus 1, and all the remaining structure constant in this integral cohomology ring of this divisive GR24 are 0. Yeah, this explains the complete integral cohomology ring of this divisive weighted GR24. Yeah, that's all these results can be found in this paper. Actually, I am writing this is in preparation also.
Are there any questions? So I didn't follow, but is there a weighted Grassmann? You have your definition of weighted Grassmann. When I studied this with we had our definition. I don't understand, but you were saying that there is your weighted Grassmann, which is not of our fault.
Yes,
Is that correct?
yes. Because that is correct. Because if you look at, okay, no, maybe the next slide, where it is. Yeah, maybe if you look at this vector, like 5, 1, 4, 3, 6, 2, this is a Fluker vector. Like you can check 5 plus 2 equals to 7, 6 plus 1 equals to 7, 4 plus 3 equals to 7. For this vector B, if we consider PL24, and then the weighted B action weighted B action defined in 1, this PL24 will be stable with respect to this action. And we can define PL24 quotient by this equivalent relation, and that relation defined by this. The equivalent relation defined by this. Because we have seen here, like I have explained here that an element, not this. The condition is like if t to the power b0 z0, t to the power b1 z1, or t to the power bm zn, that will be again in p and kn for vector b0 to bm if and only if this condition satisfies, and that is true when brj plus bsg is constant. And for these conditions, and for this, what is that? Yeah, for this case, this is a Fluker vector. Now I have proved that for a Fluker vector b, we can find w and a, like w is in zn and a is in z, but we cannot get this both thing positive non-negative together. Like we cannot find W is in Z greater equals to the n and A is in Z greater equals to 1. Because if we look at the second component, here it is 1. So if I like W1 plus W3 plus A equals to 1. If we want to get A greater equals to A belongs to Z equals to 1 and Wi is positive, the only choice of A is 1. Then W1 plus W3 is 0. You are
Yeah, okay.
I should write it here.
Another question. So you have this module basis, like children. Do you have geometric construction of those parts? Do you have a geometric construction of this basis, or you just have cohomology?
No, actually this is we have in the earlier we have constructed a Q cell structure of this weighted Grassmann. I mean that is also similar to Q cell structure. For this Q cell structure, for this Q cell, we can consider the closure, then the corresponding equivalent cohomology ring, in the corresponding element in the equivalent cohomology ring, that will give these conditions. I mean like those elements, those are on this, those elements. I mean the first condition will come by, we will see for this lambda I, like cell corresponding to this lambda I, which points, which fixed points are there on that cell. And then if we consider the corresponding element in the equivalent cohomology ring, that only those coefficients, it will be non-zero. I mean every conditions will come from there.
Come back.
Yeah, so Joseph, can you hear me?
Yes.
Okay. So is it okay to start 3 o'clock? Is it okay to start 3 p.m.?
Sorry.
Is it okay to start at 3 o'clock, 3 p.m.?